Hello and welcome to this short presentation related to spring stiffness. And within textbooks and reference books, spring stiffness is often denoted by the letter K or the Greek letter lambda. In these notes I'm going to use K. The formula for spring stiffness is K is equal to P, that's the applied force or load, divided by the extension, usually denoted by the lowercase Greek letter delta. So the original length, the unstretched length of a spring added to delta produces the final length of the spring. We're interested in spring stiffness for various design purposes. For example, if we're designing centrifugal clutches, where the friction surface's movement is a function of spring stiffness, or also in friction clutches, where the friction forces between the plates can be sometimes again a function of spring stiffness. So let's consider spring stiffness. Firstly, spring stiffness is a characteristic of a spring. As mentioned already, when designing with springs, we not only need to know their initial diameters and their initial length, but also the stiffness of the spring. Within a laboratory experiment, for example, spring stiffness is determined by loading the spring with weights and then measuring the resulting extension that occurs. So on the left hand side here is a photograph of a laboratory experiment. Here's the spring. This is an extension spring. You can also buy compression springs, but in this experiment it's an extension spring. And essentially weights are added to the end of the spring, applying a load or force P in this case. And on the graduation scale here, the deflection is measured, usually denoted by the symbol delta. So as weights are added to the bottom of the spring, we can measure the resulting extension or deflection, so we can plot the load or force P in newtons against the deflection, which is an extension in this case, and that's in meters. So here's our plot of load against extension in this case. Now the slope of the line relates to spring stiffness. So I'm using symbol K here in my notes, but some textbooks will use the Greek symbol lambda for spring stiffness. What we usually find is the load against extension diagram produces a linear line commencing from origin here. So in this case, the slope or the gradient of the line K evaluates to 3,815 newtons per meter, using the unit stated on the axes here. So that would be the spring stiffness of the extension spring shown in the figure on the left. Spring stiffness considerations continued. So we know that K is spring stiffness, and that's usually measured in newtons per meter, or of course stated as Newton meters to the -1. But you will find in some reference sources spring stiffness stated as newtons per millimeter or Newton millimeters to the -1. The axial force or load, labelled as P, would be in newtons. The deflection delta, which can be an extension or a contraction, will be in meters or, of course, millimeters. To calculate the extension or contraction delta, it's simply the final length of the loaded spring and subjected to an applied force P minus the original unstretched length of the spring L0. That's the unloaded condition. Of course, the above spring stiffness equation can be rearranged. If we want to find the actual force in the spring, then that's P is equal to K multiplied by delta. And returning to the previous slide related to the load extension diagram, the equation to the line could be written as P is equal to 3,815, that's the spring stiffness K, multiplied by the extension delta. And that would give the load or the force P in terms of newtons. Let's consider a few exercises from our notes. Exercise 4F. A spring of negligible mass, so we can ignore the mass from the question, is subject to an extension delta of 50 millimeters, and that's under a load applied P of 100 newtons. We're asked to calculate the spring stiffness K. The answer is shown in the bracket here. Using the previous equation for spring stiffness, I would encourage you to start the presentation and attempt exercise 4F, but the solution is shown on the following slide. So exercise 4F, here's the solution. So extracting the information from the question, spring extends 50 millimeters when subject to a load of 100 newtons. We're asked to calculate the spring stiffness. So here's our calculation for spring stiffness K. Using the formula from the previous slide, K is equal to P divided by delta. On the question, the force P is 100 newtons and the extension delta is 50 millimeters, which I've converted to meters here, so 0.05 meters. Evaluating the spring stiffness is 2000 newtons per meter, or that could be written as 2 kilonewtons per meter. Exercise 5F, there are two parts here. Part 1, we're asked to convert a spring stiffness of 1.5 newtons per millimeter into newtons per meter. And in part 2, we're given a spring stiffness of 1.5 kilonewtons per meter, extends 60 millimeters and subjected to an applied load. We've got to calculate the force or the load in the spring. The answers are shown in the brackets for reference. I would encourage you to stop the presentation and attempt exercise 5F. The full solution is shown on the following slide. Exercise 5F, part 1 asks us to convert the spring stiffness from 1.5 newtons per millimeter into newtons per meter. So given that K is 1.5 newtons per millimeter, using a unity bracket here, unity is 1000 millimeters in 1 meter. Remember, these are cancelling unity brackets, so the millimeters on the top cancel with the millimeters on the bottom here, and that leaves us with a spring stiffness of 1500 newtons per meter. In part 2, we're asked to calculate the force in the spring. So from our equation that K is equal to P divided by delta, we can rearrange for P. P is equal to K multiplied by delta. From the question, the K is 1500 newtons per meter and the extension is 0.06 meters. That evaluates to a force in the spring of 90 newtons. And here's a brief extract from a spring manufacturer's catalogue. This extract relates to extension springs. This diagram relates to the nomenclature shown below of an extension spring. The wire diameter, lowercase d, shown here. The outside diameter of the spring, shown here. The mean coil diameter, shown here. And the free length, shown here. What is termed the rate of the spring here is actually the spring stiffness. Here is a further extract of the extension springs from the catalogue. These are actually made of stainless steel, it states. And here is the geometry and spring stiffness in terms of metric dimensions. So for a given wire diameter, we have two different mean diameters, a range of free lengths for different mean lengths of spring for each mean diameter. And what is termed the spring rate here is actually the spring stiffness. Denoted as P divided by F in this particular catalogue, having the units of newtons per millimetre. So here is the array of various spring stiffnesses. That's just typical information you'll find via the internet or various reference sources related to characteristics of springs. So springs are a specialist manufacturer. You do not make your own springs, you buy them from a specialist, and they will supply you with the range of information as shown on this slide. And of course this information is used for design purposes related to geometrical considerations and loading considerations in service. I hope this brief presentation related to spring stiffness has been of interest to you, and thank you for viewing.